Okay, so before starting actually the very important lesson of the chain rule in derivatives, I want to complete what is left over. So today might be, if I have time, I will start the new lesson as well, but these are all very important topics that I want you to know. The first thing that I want you to know is that there is another formula for the derivative. You might see them in different books. Okay, it's very important. I want you to at least have a flavor of that formula as well. So you know that if I have a function f whose domain is df and I have a in the domain of this function, then we define the derivative of this function at a to be the limit of f of a plus h minus f of a divided by h goes to 0. Okay, so that's the formula that we have used so far. Yes? There is also another way of writing this formula. I think I have seen it in the formula sheet. I am not completely sure about that. But even if that's not there, you see slightly different formula in different books. I just want to you'll be familiar with that formula as well. So this important thing is that when you use this formula, you see h always goes to 0. Yes. Now what happens, we can change the name of this function. So for example, I can write a plus h and name it x. Okay? Then what happens, sorry. Can you see now? Okay, a plus h is equal to x. And then what happens when h goes to 0? When h goes to 0, this will imply that x goes to, can you tell me? X goes to a, yes, exactly. So instead of saying h goes to 0, if I choose to name a plus h as x, I can say that, okay, when h goes to 0, my x goes to a. Okay, then what happens? What is h now here? H is x minus a, if I move a to the left, yes? And then I replace everything back here. So then the derivative of f prime of a is equal to the limit. Instead of saying h goes to 0, I write x goes to a. And instead of f of a plus h, I can write f of x minus, a is just a number, a constant, so I keep it like that. And instead of h, I can write x minus a. In many books, you see this as the definition of the derivative. But I just want to know that these are the same formulas, okay? And then you need to know the differences. Here, if you use this formula, sometimes x goes to a. If you're calculating it at 1, x goes to 1. If you're calculating at 2, x goes to 2. But in this formula, h always goes to 0. So that's also, I want you to know. Let me change this. Okay, and I want to just give you one example to see the difference between these two, and then you can choose which one you prefer. So for example, let us take this very simple function f of x to be x squared, and then I want to calculate f prime of 1 in 2 different ways. Once using this formula, another time using this formula, and then you see how this will work. So if I want to use that, this you already know, so let me just do it quickly. So f prime of 1 is equal to the limit of f of 1 plus h minus f of 1 divided by h goes to 0. So then this becomes the limit h goes to 0. What is f of 1? F of x is x squared, so f of 1 is just simply 1 squared, which is 1. And f of 1 plus h, it means that I have 1 plus h to the power of 2. And then I have to calculate this limit. For example, I expand this one, becomes the first one to the 2 times the first one times the second one, plus the second one to the 2, and then I have minus 1 at the end, divided by h goes to 0, and then this one and that one are cancelled, so what you get is the limit of 2h plus h squared divided by h goes to 0. I factor an h out, and then you see that these h's are cancelled, so the answer is 2. So what I get from this formula, that is 2. Yes. I'm just comparing the formulas. Of course, nobody calculate now this in this way unless it is mentioned, use the definition. If you are not allowed to, if you are not forced to use the definition, you just simply take the derivative 2x and then replace x with 1, which gives you 2. Okay, but sometimes you are asked to use the definition to calculate something. You can choose this one, or if you want to, you can choose this one. So let us calculate this using this formula now. So f prime of 1 is, according to this formula, it is a limit. Instead of h goes to 0, I have x goes to a. But a in this case is 1, so x goes to 1. In the denominator, I have x minus my number a. My number here is 1, so it becomes x minus 1. But the good point is that you don't need to replace f of x with something else. F of x is just given to you x squared. You just simply write x squared. And then you have minus f of a, which is f of 1, which is exactly 1. Yes, is that understandable? So the good point about using this formula, especially when you want to calculate the derivative at a point, you see, if your function is a little bit complicated, you need to replace it by a plus h, and then you have to do some calculations. But here, you don't need to do that calculation. Okay, x goes to 1. Of course, the denominator is 0, so it means that I need to get rid of these zeros somehow. Then it is a conjugate pattern, so you can factorize it. This becomes the limit of x minus 1, x plus 1, and then you have x minus 1, and x goes to 1. And this x minus 1 and that one are cancelled. And then when you put x equal to 1, 1 plus 1 is the same as 2. Yes, so that's up to you which one to use. But it was important to see, because most of the, especially university texts, they also have this formula. So I want you to know that this is not a new definition of derivative. That's just a simple formula written in a different way. Okay? So that is one thing. Another thing is the notion of differentiability, that you had it in Math 3C a little bit, but this is an advanced topic. I don't want to elaborate on that so much, but I want you to understand what is the meaning of this. Because sometimes, if you are familiar with limits, sometimes the limit does not exist at all. Okay, in that case, if the limit does not exist, it means the derivative does not exist. And if the derivative does not exist, we say that the function is not differentiable at that given number. Okay? I just want to talk a little bit about that. At some point, you have to learn this. I remember this was an example in Math 3C, at least in the Oracle book. Okay, so to give you a flavor about that, let me consider this very simple function, f of x equals to absolute value of x. And then I want to talk about the derivative of this function at point 0, if possible. Okay, so I want to calculate the derivative of this. First of all, this simple method does not work here, because in this case, even if you don't like this, you have a formula for the derivative of x squared, which is 2x. You do it, and then replace x with 1, you get 2. But there is no formula for the derivative of absolute value of x. You know absolute value of x, yes? What is absolute value of x? For example, absolute value of 2 is? 2. Absolute value of minus 2 is? 2. So it means that, this is a little bit confusing. Absolute value of x is equal to x itself if you know that what is inside the absolute value is non-negative. Yes? But if you know what is inside the absolute value is negative, then the answer becomes negative x. So this is the way that you need to know the absolute value, okay? So this definition of absolute value is important, yes?
Mr. Rowan,
Yes?
couldn't we? No, wait, that wouldn't work.
Okay. So you want to calculate, you want to talk about the f prime of 0. And let me write this new formula that I just introduced to you. Do you remember? F prime of A is defined to be f of x minus f of A divided by x minus A when x goes to A. Yes?
Couldn't you define the absolute value of x as square root of x to the power of 2?
Yes, we can define it. But that's a tricky way because the square root of x squared is defined to the absolute value of x. So, because when you say, no, I would prefer to define it in this way. This is the difference. Do you have any question?
No, it's just the same.
Okay. No, the consequence of this definition is that square root of x squared is absolute value of x. Okay? So it's square root of x squared. If you write x, it is not right. Because, for example, if I write a square root of minus 2 to power 2, does this make sense? The answer is yes, because minus 2 is negative, but when I raise it to power 2, it becomes 4. Square root of 4 is defined, and the answer is 2. But if you just naively say that I would say this one and this one will cancel each other and write minus 2, this is clearly wrong, yes? You need to write absolute value of minus 2, and the answer becomes positive 2. So if your question is that, this is the definition of absolute value. The consequence of this definition is the square root of x squared is absolute value of x. Okay, but let me use this formula to talk about the derivative of this function at this point. So what should I write? Let me be patient a little bit. F prime of 0 is equal to the limit of my function, which is absolute value of x, minus f of, let me write everything, sorry. First, I replace a with 0, so it becomes f of x minus f of 0. X minus 0, x goes to 0, because here a is equal to 0. Now let me replace everything according to my function. F of x is absolute value of x. F of 0 is absolute value of 0, and then x minus 0 is just simply x. X goes to 0. So then what is this limit? What is absolute value of 0? It is 0. And then this one minus 0 is just absolute value of x. And then divided by x, x goes to 0. So this is a very simple and good example to show that don't take this for granted that every limit exists. This is not the case. For example, what is the limit here? What is the limit of this function? The limit of this function does not exist at all. Okay? The reason is that when you say that x is close to 0, it means that x is negligible, but it is not clear. Is it positive and negligible, or is it negative and negligible? Yes? And the problem is that absolute value is different when this is positive or negative. So this means that if I want to answer this, I have to restrict myself to two sides of 0. This is, I don't know, have you seen this symbol before, the people who had a lesson with me? So this is limit of x goes to 0 from the right-hand side. This doesn't mean positive or negative. This means that if this is your x-axis and this is 0, it means that I am getting closer to 0, but from positive numbers. So I am getting close to 0 from this side. Okay, let us see what happens. This becomes the limit. When I am guaranteed that x is negligible but positive, I can take this absolute value sign away because x is positive, so I don't need it at all. X goes to 0 from the right-hand side. And what is this limit? This is exactly equal to 1. But when I change my perspective and I send x to 0, I want to make x negligible again. But this time, I restrict myself to get closer and closer to 0 from the left-hand side. So then what happens? Let me write it here. So this becomes the limit of absolute value of x, and x goes to 0. This negative sign that I put here means from the left. This positive that I put on top, it means from the right. But what happens for absolute value here? Because when x goes to 0 from the left-hand side, it means that x is negative. When x is negative, if I want to remove the absolute value, I have to apply an extra negative sign. So then this becomes the limit of minus x divided by x. X goes to 0 from the left. And if you calculate this limit becomes negative 1. So it means that if I get closer to 0 from the right-hand side, the value for the limit becomes 1. And if I get closer to 0 from the left, the value for the same limit becomes minus 1. And I don't know have you learned this in Matematik or not, but take it for granted. If the left-hand side limit and the right-hand side limit does not match, then it means that the limit itself does not exist at all. Okay, so because these two numbers are not equal, then this implies that the limit of absolute value of x divided by x, x goes to 0, does not exist. Okay, and what is the meaning of this? It means that my function, so it means that f prime of 0 isn't any number. It's not. It does not exist at all. So if I ask you what is f prime of 0, you should say it doesn't exist. Okay. Then the terminology that we use, we say that this function is not differentiable at 0. Okay. So this is the terminology we use. The function. So the function. So f prime of 0 does not exist, or in other words, f of x equals to absolute value of x is not differentiable at x equal to 0. So this is the terminology. I just want you to know about that. This is quite advanced lesson. I don't know, in Origo book it was discussed in Math 3C. I don't remember if it's also discussed in Math 4 or not. But this is an important idea that I want you to learn that. And I want to talk about how you can realize, by looking at the graph of the function, you can realize immediately at which points the function is not differentiable. Okay, this is important to know. There are 3 types of points that the function is not differentiable at. Okay, if I draw the graph of this function, okay, so if you use your calculator to draw the graph of this function, it is like this. The bisector of this quadrant together with the bisector of this quadrant. This is my function f of x equals to absolute value of x. And then where is x equal to 0? X equal to 0 in this case is here. Okay? So if you have a sharp point, okay, I will talk a little bit about what do I mean by sharp point, but you have a feeling that this is a sharp point. If you have a sharp point on the graph of the function, you need to know this, that your function is not differentiable at that point. For example, this point is 1. If I go here, do you think that the derivative of this function at 1 exists? Yes, because this is not a sharp point. Yes, but this 0 is a sharp point, so it is not differentiable there. Your function is not differentiable there. And the reason is clear, because let me just tell you a little bit more. Because when you send x to the 0, you are calculating the slope of the tangent line. When you are actually on the right-hand side, the slope of this line, which is called the tangent line itself, is equal to 1. But immediately before that, the slope of this line is negative 1. So the slope at this point is not defined, because a little bit on the left, the slope is negative 1. Suddenly, the slope becomes positive 1. Okay, so this is the meaning, intuitive meaning of that. Another type of points where the function is not differentiable are the points at which the function is discontinuous. So for example, the graph of the function comes up to here, and suddenly at this point breaks into another part, and then it starts from here, for example. Okay, so this is supposed to be, this is not part of the graph, so I just want to make sure you understand. For example, if this point is A, okay, then if this is the graph of f of x, if I ask you what is f prime at A, you would say this does not exist. Because exactly at that point, the graph is breaking into two pieces. This is called discontinuous function. The function is discontinuous at the point. So then, of course, this is a theorem, but I just want you to know about that. Okay, so the derivative of this function at this point does not exist. F is discontinuous at x equal to A. Therefore, when I say therefore, it is a theorem. I just don't want to prove it. That's not at the level of your lesson. Therefore, f is not differentiable at x equal to A. So this is the second category. The first category are sharp points. If I want to draw another type of sharp point, this is also sharp point. Yes, so this point is also a sharp point. Yes, so any point that is a sharp point intuitively, the function is not differentiable there. This is one category of points. You need to remember it. Another category of points are the points at which the function breaks into two or more pieces. Okay, so that is also a discontinuous function. So the function is not differentiable, but there is also another one that you might be able to guess. There's the third category. Can you see what will happen? Another category, can you imagine what would be the other category? Because remember, what was the geometric intuition about derivative? It was the slope of the tangent. Yes? Yes?
If the section is undefined.
No, section is not on, of course, if this, because the derivative is always defined for where A is in the domain. That's not the case. Yes? No, yeah, okay, exactly the other way around. Because horizontal, what is the slope of a horizontal line? 0. But what is the slope of a vertical line? It is infinity, so it means doesn't exist. So it means that if the graph of a function is in a way that if you draw the tangent line, it becomes vertical, at that point, there is no derivative because the slope is infinity. And you can also imagine that, yes, for example, I can have a graph like this. This is a terrace point as well. So for example, I come here up to here. It's hard to draw it, but you understand what I mean. And then you go there. And then assume that at this point, I want to draw a tangent line to the graph. The tangent line to the graph becomes this, yes? And this is a vertical tangent. And if I ask you what is the slope of this orange line, you would say it doesn't exist because it's a vertical line. So remember, these are 3 points. You need to remember that the function is not differentiable at. One category, sharp points. Second category, discontinuous points. The third one, the points at which the tangent line is vertical. Yes? For example, this function, is this function differentiable at this point? The answer is yes, because the tangent is not horizontal. But exactly at this point, the tangent to the graph becomes horizontal, vertical, I made a mistake, vertical, and this is not differentiable. So 3 category of points, the function is not differentiable. This is a very important lesson to remember. Okay, any questions so far? Another thing that is still left, I want to talk about, and that's another interpretation of derivative. Do you remember what was it from Math 3C? One interpretation of derivative was the slope of the tangent line. Of course, the slope has a meaning itself. Yes. What was the other interpretation? If you want to say the notion of the, if you want to explain it in words,
The rate of change.
the rate of change. So these are two things that you need to know about the derivative. Okay, so do you remember when I started the derivative lesson here? So we had a graph here, y equals to f of x, the graph of a function, and then this point was a, and this point, for example, a little bit after that, it is a plus h. Yes? And then what happens? Assume that this is the function. Here, the quantity y depends on another quantity x. This is the meaning of being a function, yes? So it means that if I start varying x, if I start changing x, the variable y also starts changing following the changing x, yes? If assume that I am standing at this point, then I start increasing, for example, in this picture. Increasing is not matter, just changing. Here in this picture, I'm increasing. It might be decreasing, okay? So assume that you increase the value of x from here to here, okay? This change usually is called delta x. It means the change that I am making in the x value. And let us measure somehow what happens for the change of the second variable y. Yes, what happened? In the beginning, when I was here, the y variable was this. And then when I go here, the new y variable is a little bit bigger in this case, of course. Sometimes if the function goes down, it becomes smaller. But at least this is my old new variable y. This is, let me write it y final. And then this is y initial. So if I ask you how much is the change in y, delta y, what should I write? It is the y final minus y initial. Yes? And then if I want to measure it in pictures, so this is exactly delta y. Do you agree? Because this is yi, so this is also yi. So y final minus y initial, it becomes exactly this way. Yes? And then if I ask you, can you write a formula for delta y? You would say yes, because this is y final minus y initial. What is y final? Y final is f of a plus h. What is y initial? Is f of a. Yes? This is f of a plus h minus f of a. And then do you remember what was the limit? Delta x is the same. X final minus x initial. X final is a plus h, x initial is a, so it becomes h. And then do you remember the formula I just wrote here? So f prime of a is f of a plus h minus f of a divided by h goes to 0. Now you can write it as, instead of h, I can write delta x. Instead of h, I can write delta x goes to 0. Instead of f of a plus h minus f of a, I can write delta y.
Yeah.
Yes? So now what you see here is that the derivative is the rate at which the y is changing with respect to the change of x. Okay? But when, of course, this change of x is very small. If you don't have this limit, delta y divided by the delta x is the average rate of change. How much the function in average changes in this big interval. Yes? But if I make this interval shorter and shorter, I am getting closer to instantaneous rate of change. So in the limit, when delta x goes to 0, at that point, I will get the derivative. So this gives me another very important interpretation of the derivative of a function at a point. So let me write it here for you. Do you feel also painting is smelling or something?
Yeah, it's slowly.
It's really annoying because it's coming from the. Okay. Okay. So let me write this statement for you. So let f be a function that is differentiable at x equal to a. then f prime of A, number one, is the slope of the line tangent to the graph of the function f at the point on the graph whose x coordinate is A. Yeah, let me underline this here. So this is what we learned before. So let me just put this in a picture so that you can remember it. It is very important to remember this. So if I have the graph of my function, and then you have this point, x coordinate is A. If you draw the tangent, okay, the k value for this tangent is f prime of A. So this is the picture, you should have it in mind. This is one interpretation of the derivative. Another interpretation is exactly what I have written here. So what is that one? F prime of A is the instantaneous rate at which y is changing at the point, when x is equal to A. It's better to write it this way. That is also another interpretation. Any questions so far? But there is also something that I want to mention. Usually when you want to work with abstract mathematical functions, x and y are pure numbers. But for example, whenever you want to have as a rate, interpreted as a rate of change, you usually have two different quantities. For example, the displacement versus time, or I don't know, the velocity versus time, something like this. In those cases, you are more or less interested in talking about the derivative as a rate of change, and it means that you need to consider the units also, because here delta y is a pure number. In mathematics, I'm not measuring anything. I have pure numbers, so there is no units for this. There is no units for this, so that's a unitless value if you just simply calculate the derivative. But assume that, for example, the x coordinate is time. For example, the y coordinate is the displacement. It doesn't matter. I can write, instead of delta y, I can write delta s. Instead of delta x, I can write delta t. But delta s is measured, for example, in meters. Delta t is measured in seconds. Then the rate at which s is changing with respect to the change of time should be expressed in meters per second. Okay, so that's very crucial. If you want to interpret the derivative as a rate of change, and if these quantities are representing something which are measured in some units, it is a have to. You have to express the unit at the end. Is that clear? Okay. So let me just give you one example of this type. So, for example, if this is probably the very famous one, assume that you have a bacterial culture, I would say, yes, if I'm right from the English point of view. So, assume that you have a bacterial culture, and then there is a model for the number of bacteria that is inside that culture. For example, I don't know, you start from this crude model 10, or let me write 100, e to power 0.8 t. Okay, so assume that you have a model, you have a bacterial culture, and the number of population of the bacteria inside that culture is somehow modeled by this formula, in which n is the number of bacteria in the culture, yes, and t, for example, is, so we can say the number of hours. I don't know how realistic is this one, this model, forget about that. The number of hours after the investigation has started. So now, for example, if I ask you, calculate the derivative of n prime equal to 5, okay, n prime at 5, it's easy to do. Let us do it, for example, here. How should I calculate n prime of 5? I have a function. I need to take the derivative of that function. After it is done, I replace the variable with 5, and then it becomes a number, yes? But you, of course, you know what to do with this. Is a simple function. I talked about this last time. So the first thing that I do, I calculate the derivative of the function n. So what happens? It becomes 100 is just a multiplicative constant, so I don't care about it. And this is playing the role of k. Do you remember? This k goes down, multiplied by 0.8, and then I have to repeat the whole function in front. That is the derivative. And then let me multiply this 100, make it a little bit simpler. So the derivative is how much? Is 8t to power 0.8. And then if I ask you to calculate n prime of t, what happens here? It becomes 8t e to power 0.8 multiplied by 5. But then this has a unit now. So you shouldn't leave it like this, because n prime of t is the, sorry, this is not t, this is 5. So this is the rate at which this quantity n is changing at this quantity, when this quantity t is equal to 5. So this is the rate at which the number of bacteria is changing when the time is 5 hours exactly after the research has started. Yes? Is that understandable? So it means that this should be written number of bacteria or whatever, number of bacteria per hour. So this is very important to write these units at the end. So n prime of this is this one. If you want, of course, you can simplify this a little bit. I don't know, 5 times that is e to power 4. It doesn't matter. So number of bacteria per hour. So that would be the answer. So what is the interpretation of this number that we got? It means that the population of the bacteria is changing at this rate when time is 5. Okay? A little bit later or a little bit before that, this is not the rate of change. This is the instantaneous rate of change of the number of bacteria when time is exactly 5 hours after the research has started. And if you calculate this at another different time, you might get a different number, okay? So that is the point. If you have a curved line, it is completely clear that if I go from this point to that point, the slope is changing. And the slope is the rate at which it is changing. There is only one type of graph that the slope remains the same all the way around. And what is that? Just a straight line. The slope of the straight line is not changing at all. It doesn't matter where are you measuring this slope. But if you have a curve, it's very important where you are doing this measurement. From a point to another point, the rate at which this is changing is different. Yes? So that's also, we had it in Math 3C. I just want to talk about that here. There's also one point. There are some notations that I want to understand about them. They're also very ubiquitous in derivative. There are different symbols. Okay, the first symbol, if I have a function f, then its derivative is denoted by d of f. Okay, so let me write this in this form. Y equals to f of x. For denoting the derivative, I can use y prime. That's okay. Y prime is the derivative of f. I can use f prime of x. That's also okay. I can use this symbol, which is also used in Europe. I put capital D for derivative, and then I put f of x in front. That is also very important to know. And there is also a little bit of strange notation, which is called Lightness Notation. Instead of writing it in this form, people sometimes write it dy dx. First of all, this is motivated by delta y by delta x. Yes, something like this. This is called the Lightness Notation. For derivative. It's a little bit cumbersome because when I can use something so simple, why I should bother to write something like this? Yes, the answer is yes. It might be, it doesn't necessary, but there is another point here, which is also discussed in the book. I want you to know. Here, when I talk about the derivative, it means that my variable is x. It's so obvious that I don't need to emphasize that my variable is x. But sometimes, for example, I am facing this type of functions. For example, I have y equals to a to power 2 times x to power 3. If I ask you to calculate y prime, of course, in principle, we have get used to this idea that x is always the variable, other parameters are constant. So if I ask you the derivative of this, can you answer me? What's the derivative? What's the derivative? Pardon? A squared times x to the 3. Yes?
3a. 3a squared x squared.
Exactly. But the reason that you are doing this, you are presupposing that x is variable and a is constant. When a is constant, a to power 2 becomes a constant, so you can give it you can assume that this is 5 or whatever. Okay, it's a constant. And if you want to take the derivative of this combination, you just don't care about the constant. You take the derivative of that one and then multiply it by your constant. So we have done that one. Of course, but if you go a little bit more in more advanced mathematics, sometimes we can have different variables involved in the same function. Okay? So for example, in that case, it is better to use this symbol. So here, if I write dy dx, then this answer is correct. But it might happen that I am taking a as my variable, then I would write dy dA. It means that take the derivative of the same combination, but this time assume that your a is your variable. Okay, now can you answer me, what is this one? 2a x cubed. Yes, so it becomes 2a x cubed. So do you understand what's the difference? So even though you don't need to be worried about this at all, but I just want you to know about this because it is expressed in the book. When we talk about functions, we usually always get x as the variable. Okay, even if it's not mentioned. If I want a to be your variable, I have to write it in Lightness notation so that you understand the point is that a is the variable. Is that clear? That's only reason that is useful for the time being. Another thing that I want to talk about is the notion of higher derivatives. And you had it in Math 3C as well. So what is the meaning of higher order derivatives? Okay, so it means that I have a function, I do the derivative once, I get a new function. This function is derived from the previous function, so this is why we call it derivative. Yes? And now, this is a new function on its own. I can do another derivative. I can differentiate the new function once more. Okay? Then the function that appears is called the second derivative of my original function. For example, if I have a y equals to x to the power of 3, for example. Okay, so let me make it 4 or 5, because I want to also teach you the notation that we use. If I ask you what is y prime, it's simple. It's 5x to the 4. But now, forget about the name of the function. This is also a function. If you take another derivative of this, it becomes 20 x to the 3. Yes? This is the first derivative of this, but this is called the second derivative of that. And the second derivative is denoted by y double prime. So when we say y double prime, it means take this derivative 2 times. And then we can have another derivative, which is called triple prime, yes? Y triple prime is 60 x to the 2. But if I want to go further, it is the convention that we don't write with 4 dashes. This is not a standard way of doing that. People put 4. But the point is that if I just simply put 4 here, it will be confused with the exponent, power, yes? This is the convention. You put a pair of brackets around that. So when you say y, this is called the 4th order derivative of y. It means that take another derivative of this one. What's the answer? 120x. So now if I want to take another derivative, I have to write it in this way. And then it becomes 120. And what do you think about derivatives coming next? All of them will be 0. Because if I took one derivative, take one derivative, it becomes 0. After that, everything becomes 0, yes? So it means that you can write fyn, the nth order derivative is 0 if n is greater than or equal to 6. And that is also one important question. Can we find a formula for nth order derivative of any given function? The answer is not, but sometimes we can. Okay? Is that clear? So for example, let me ask you one question. If I give you this function, I think it's easy to guess. Yx e to power 2x, for example. Can you tell me what is y to the power 6th order derivative? This is one of those functions. It is not hard to answer. But if I have a function which is complicated, it becomes very, very complicated if I want to answer these things, because every time the function is not getting simpler. I gave you 2 examples that the functions become simpler or remains in the same form, more or less. But sometimes functions changes very differently. Yes, anyone? Yeah.
Is it 32?
32 is that right?
To the power of 5.
Yeah. I was thinking 2 to the power 6, isn't it? Because if you take the first derivative, if the number of derivative is 1, you have a 2 down, yes? Do you agree with this? This is the first derivative. If you take the second derivative, what will happen? Another 2 will go down. Multiplied by this 2, it gives you the second power. Agree? So then if I go to the third one, another 2 goes down. So this becomes 2x. So it is clear that if I continue this process, it would be 2 to the power 6 e to the power 2x, which can be written as 6 to 4 e to the power 2x. Okay? So we will come back to these things, but this is something that I just want you to know about the notion of the derivative. In practice, this is enough for Math 4. The first derivative, the second derivative, the function, the first derivative and the second derivative. But this is also discussed in the book. This is not hard, but for practical reasons, this is important. Because the point of knowing derivative is being able to draw the graph qualitatively so that we can highlight the main points on the graph. And now we learn that only the derivative and the second derivative are enough for having a qualitative picture of the graph of the function. Okay, let me also, this is the notation that you use. If I am using this notation, this is the notation I use. If I use the same notation, that's the same thing. F prime, F double prime, I don't know, F triple prime, and then I can write the 4th order and etc. But this is something that you need to know. They put just the normal power. So for the second derivative, they write it like this. For the third derivative, they just write it like that, and etc. There is no pair of brackets around that. And then the very strange notation is the Leibniz notation. So if you want if you want to take the second derivative using the Lightness notation, it means dy prime dx. Yes? So somehow, this is the idea. Y prime itself is dy dx. Yes? And then you have dx. So it seems that these two x's, this is crazy way of saying, but because these are not fractions, it's just normal fractions, but it seems that dx and dx are being multiplied, so this becomes dx to the 2. And then this is the derivative of another derivative, so it becomes the second derivative. So this is the way that if you want to express y double prime in Lightness notation, you need to put a 2 here and a 2 here. If I want to write y triple prime in Lightness notation, then it becomes the third derivative of y with respect to x3. So that's the way that we use it. So if I want to write this notation, this one in Leibniz notation, this becomes dny dxn. Okay? Is that clear? So these are what was left over so far from those pages. And I think it's clear more or less. Is it? Okay, we have 20 minutes. It's better not to start the next lesson because the next lesson is a very, very important lesson. So I will stop here, but I will continue on Friday if it is not affected with physics test. If it is affected, we will continue next week, okay? But the next lesson is a very, very important lesson. Let me warn you, be prepared for that lesson. If you don't learn that lesson, you will not learn anything from Math 4 from now on, okay? So even if you are somehow slightly sick and you cannot join, please send me a message so that I can broadcast it for you. You can just please don't try not to miss that lesson because that's a very important lesson and that's completely new. No questions? Okay. So I will stop here.